In this video, we're going to talk about Newton's third law and go through how to draw free body diagrams for Newton's third law problems. So Newton's third law says you may have heard it this way, for every action, there is an equal and opposite reaction. And so by action and reaction, you can replace those with the word force. So for every force exerted by one object, there's an equal and opposite force exerted on that object. So action and reaction are just forces. And another way to state this is that forces come in pairs. And so sometimes they are called action-reaction pairs. Okay, so you never have one force without another. And then the two forces in these action-reaction pairs, so in action-reaction pairs, they always act on different objects. Okay, so two different objects. And then only one force, only one of these forces, so only one of the action or reaction forces from the action-reaction pair act on each object. Okay, so one force acts on one object, the other force acts on the other object. So let's take a look at these action-reaction pairs. So let's say we have two objects. We have a box A and it's touching a box B, and let's say they're exerting forces on each other, so they're pushing on each other. Well, then we'll call this, where B meets A and is pushing to the left, we'll call this the force from B acting on A. And if there's a force from B on A, that means that forces occur in pairs. So A must be exerting a force on B. So this is the force FA on object B. Now, the relationship with these, they're equal and opposite. So this may be written as FA on B is equal to minus FB on A. Okay, so this minus sign just refers to the fact that they are in the opposite direction. Okay, so these forces in these action-reaction pairs have the same magnitude but different directions or opposite directions. Okay, and when you have the vector hat on top of these forces, then you have to put in that direction. But you may also see it, and so just not so you don't get confused, if you see FA on B without the vector hat, well then we don't write the minus sign, because when we drop the vector hat, it means we're only talking about magnitude. And so these have the same magnitude. And so be careful when you're looking at this and whether or not there's a vector hat on top of the force or it's missing and they're only referring to the magnitude. So now let's do an example where we look at the free body diagrams for two interacting objects. And so we'll need to draw a free body diagram for both. And sometimes it is easier to draw one free body diagram before we draw another. And so I'll start by drawing a free body diagram for object B. Okay, so I'm going to draw my axes rotated. So this will be my y-axis and my x-axis will be going down. And now if I look at all of the forces acting on object B, then object B has mass, so it will have a weight. So I'll draw that vector straight down. We'll call it W sub B. It's also touching the surface of this ramp, so that means there must be a normal force. perpendicular to the surface. So that's going to be straight up, keeping the block B from going through the surface. Let's call that M sub B. Okay, well there's also this block A that is making contact with object B from the top. So that is a surface contact. So there must be another normal force, but this time it's from object A. So we'll call this the normal force from A on B. Okay, then we have a cable on the left-hand side. So I'm going to draw this dot a little bit bigger. It's pulling object B up the ramp, so we'll call this the tension of, well, this cable is wrapped around and it's originating from A. So we'll call this the tension from A on B. And then we have some friction forces. So this is a rough surface. And so since B is going to be sliding down, that must mean that there is friction, kinetic friction, that is going up the ramp. So this is a force of kinetic friction on object B. But not only that, we said it was also in contact with object A. If object B slides down, that means that there is friction from A that is also up the ramp. It is sliding down across the surface of A. So there is yet another friction force. This is going to be the friction, kinetic friction, from object A on object B. Okay, so we have quite a bit of forces going on in this problem. So I want you to notice two things about this free body diagram. You have two types of forces. You have forces from object B interacting with its environment, so the ramp. So there's a normal force from the ramp. There's a weight where it's interacting with the earth, so the earth is pulling on object B. And then this is also from the ramp, the friction, where it's trying to slide down. And then all of the other forces have this A on B. So these are all the forces from block A acting on block B. Okay, so as you pull A, it's going, the tension in the cable is going to pull on B. As you move B across A or A across B, there's going to be friction. And then since they're on top of each other, there's going to be a normal force. So those are all forces that are from A onto B. And so all of these forces are going to be part of our action-reaction pairs between the two objects A and B. So now I'll draw the free body diagram for object A. So I'll zoom in a bit. So this will be my y-axis and again my x-axis. And this will be object A. Okay, so again, I'll start with the weight. I like to start with the weight because most objects have mass, so they should have a weight going straight down. So this is the weight of A. And then there is a normal force, so it's pushing, A is pushing down on B, so that must mean B is pushing up on A. So this is the normal force of B on A. Okay, then we have tension pulling on it. So if you pull B, if B moves, it's going to exert a tension force and pull on A. So this is the tension from B on A. And then we have a friction force. So if you imagine B sliding down and across A, then the friction on B is to the left. But that's the same thing as if you hold B still and pull object A up the ramp or up sliding across B. And so if A is sliding up object B, that must mean friction is down. So that's one way to look at this. Another way is you can just look at your action-reaction pairs and you know it should be in the opposite direction. So this is B on A. Okay, so we have a few action-reaction pairs, and so I want to make a little note for every, I'll call it A on B, that we saw in the first free body diagram. We need a force B on A. Okay, so this is a way to double check your free body diagrams. We have three forces from object A on object B in our free body diagram for object B. So we better have three forces from B on A in our free body diagram for object A. Okay, so all of these are our action-reaction pairs. So the last thing that I want to bring up, in case there's a question, is why is T A on B in the same direction as TB on A? All of our other action-reaction pairs are in the opposite direction. So MB on A from this free body diagram is going up, while NA on B is going down. Likewise for the friction force. Well, the tensions are both going up the ramp. But this is because, if you think about it, TA on B is, well, this tension is being redirected by this pulley, so that changes things. TA on B points away from B toward object A, while TB on A does the opposite. It points away from A toward object B. Okay, so that's the only force in our action-reaction pairs that is in the same direction, but it's because of this pulley redirecting it. And if you think about it, it's pulling away from one object toward the other, and the other tension is pulling toward the opposite object. So they are still in opposite directions, if not for this pulley. So let's do another example. So in this example, we have this object B that is sliding down its ramp, pulling object A upward. Okay, so its ramp is a little bit steeper, maybe it's a little bit heavier. So it's going to be pulling object A up. And so again, I'm going to have a free body diagram for A. So let this be A, I'll do X up. And then I'll have another free body diagram for object B. So these are slightly different slopes, but that's okay. We can have our own coordinate system for each object. So I'm going to put object A on this side and object B over here. So I'm going to start with object A. So object A, as always, has a weight that is straight down. So I'll call this weight sub A, W sub A. And then it's going to be pulled up, so there's some tension pulling on A. Okay, so this is tension B on A. So as you pull B, it exerts a tension force through this cable on A. And then it's on a surface, so that means there is a normal force keeping object A from going through that surface. And since object A is being pulled up this rough ramp where there's friction, there's going to be a friction force from the ramp on object A. Okay, now if I go to B, B also has a weight, let's call that W sub B. It has a normal force. Now this wall is keeping B from going through it, so it will be to the right along what I have as my x-axis. Then there is a tension that is up from object A. Okay, so then this again is our action-reaction pair. But we also have another force up. If B is sliding down, then that means that there must be friction in the opposite direction. So friction is going to be up. Okay, and then again, we have one force that is A on B, one that is B on A. So these forces correspond to our action-reaction pair. Okay, in our next problem, we have, again, two objects, and I'll do object A on the top. So if we go ahead and do that, we have object A being pulled by this tension force to the left. So this is tension from B on A. So if you pulled B, it would pull A a little bit. It's also attached to the wall. Okay, then A has weight, so it is going to be straight down, so call this W sub A. There is friction, so if you pull it, object A, to the left, that must mean friction is opposing that to the right, so F sub K sub A. And then there's a normal force from the surface that A is sitting on, keeping A from going through it. So this is the normal force on A. Okay, so now we can go to object B. Object B also has weight, so WB. And then the only other force on B is the tension up. And again, if you pulled on A, that would pull on B. It would exert some force through this tension, so this is TA on B. Okay? And again, these are our action-reaction pairs. Okay, in our last example, we have an object A being pulled by a tension from its left, and then object B is being pulled to the right by some other tension. And we're going to imagine B is sliding out from under A. So I'm going to start with the free body diagram for B. So B has a weight. It's going to be going straight down. And then it also has object A pushing down on it from the top. So that's going to be another normal force from the surface of object A. And I'll call this the normal force of A on B. And then we have our tension force pulling object B to the right. So it's just the tension on B. There's a normal force from the surface keeping B from going through it. So this is just the normal force on B. And then if object B is being pulled toward the right, that means that there should be a friction force from the floor acting on object B, but it's also being pulled across the surface of A. So if B goes to the right across A, then there will be another friction force from object A on object B. Okay, so we have two frictions and two normal forces, one from the surface and one from object A. Okay, now if we go to the free body diagram for object A has a weight going straight down. It also has a normal force, so this time object B is keeping it from going through it, so the normal force of B on A. And then we have a tension force pulling it to the left, so this is just the tension on A. And if B is being pulled to the right across A, and its friction's to the left, that's the same thing as if we left B still and moved A to the left. And if A moved to the left, then the friction would be to the right, or in the opposite direction as the friction from A on B. Okay, so now we again have two action-reaction pairs. So we have this one, and we have this one. So these are action-reaction pairs. So sometimes when it's hard to see the direction of some force in an action-reaction pair, it may be easier to draw the free body diagram for the other object first. So I hope this video helps you understand a little bit more about Newton's third law and how to draw your free body diagrams to get all your forces and their correct directions. In the next video, I'll solve some problems, working problems using Newton's third law, where we not only draw the free body diagrams, but then we actually solve for unknown quantities like unknown forces or accelerations using Newton's second law. So I'll see you in the next video.